Lecture I will be explaining the concept of distribution. To understand distributions, we first a new way of thinking about functions, because the distribution is a generalization of a function. This approach can seem very abstract at first, but the benefit is that you can generalize the idea of derivatives and use these new ideas to help you to solve hard differential equations. But I focus on the theory, not on applications. The new way is to think of a function as operating on other functions. In analysis, we know that a function f from R to R is a function effect on element on real number and transform it or mapping it. He will be f of x. That's for Lx in R. Of course, this linear operator goes to scalar field, then f of x also in R. That means a function in mathematics is steady. The behavior of points. Ordinary function in mathematics is studying the behavior of point under some effect. The distribution in mathematics is different. It's studying the behavior of function under some effects. I mean, let t sub f be a function from some set to R. Now, the domain will be set of L smooth functions from R to R. That's mean we will studying the independent variables in our function will not points. They are functions. They are functions from R to R. That's mean I will study the behavior of function phi under this function t sub f for L phi in the set of L functions from R to R. The distribution is the name of distribution comes from the idea that the object distributes its effect over a function, not over a point. The distribution in general defined by the rule, the formula t sub f of phi equal to the integral from minus infinity to infinity of f of x multiplying by phi of x multiplying by dx. This is the general rule or the general formula of distribution. That's mean I will study the behavior of phi of x under the effect of f of x from minus infinity to infinity. That's mean or that implies in distribution we study the general behavior, not the special behavior. I mean, we study the behavior of function phi under the effect of function f between on L of the plane between minus infinity to infinity, not from 0 to infinity or from minus infinity to 0. On L of the plane. That's the reason of the borders. Now, this distribution is linear operator. Of course, in mathematics, the linear operator is a function f with these three conditions. The first condition, f of x plus y equal to f of x plus f of y for Lx and y is real numbers. The second condition is f of lambda x is equal to lambda f of x for L lambda in R. The third condition, f is a function from some vector space to R. F must has a domain as a vector space and range as a scalar field. Now, these three conditions we applying them on this distribution with this formula. Firstly, t sub f of phi plus psi is equal to the integral from minus infinity to infinity of phi of x plus psi of x multiplying by f of x dx. This equal to the integral from minus infinity. The integral is distributing on the addition. This a classical result in analysis. This equal to t sub f of phi plus t of sub f of psi. That is for L phi psi in the set of L functions from R to R, which is the domain of the distribution. We defined it. The second condition, t sub f of lambda phi is equal to the lambda and then the integral from minus infinity to infinity of phi of x d of x. This equal to lambda t sub phi of phi. That is for L lambda in the scalar field R. The third condition is held since the codomain or the range of distribution is a scalar field, which is R. Now, what is the natural of the domain of distribution? The set phi, the set of L functions from R to R. What is the natural of function phi? Is it has a condition, some conditions? Yes. I will be write definition. Quickly. The function phi from R to R is linear operator. It's linear operator called what? Called test function. I'll be change the color. This is important name. Test function, because we are testing it by the function f, which called the kernel of distribution. We as I say, we in distribution we study the general behavior of the test function under the effect of a kernel function f with the conditions. Firstly, phi must belong to C infinity of R, i.e. it must be infinitely differentiable, or it must be smooth. The same thing. It must be a member of this set. All of us know what is the meaning of this set. It's set of L real valued infinitely differentiable or smooth real valued functions. The second condition, SUPP, the support of phi must has elements, finite elements, and support of phi must be closed. Is closed, i.e. phi must has compact support. That is very important. Phi must has compact support. In other words, I will be write the draw here to explain geometrically what is the meaning of this. This function goes to infinity. It's the curve. This curve goes to infinity. This is not phi because the support is not little than infinity here. This function is test function because it's bounded. Then its support is compact. You must studying the general topology before watching this lecture. Analytically, this condition we can translate it in this words, i.e. there exists R is a member of real numbers where for Lx is greater than R, phi of x must equal to 0. Now the sets we define other thing. Definition. We define the set D of R. This set D of R is equal to the set of L test functions phi from R to R, where phi belong to C infinity of R, and phi has compact support. This Dow of R will be the domain of distribution. The distribution will be the function goes from D of R to R. Focus with me. If you don't understand the concept of distribution, the distribution is just the study of behavior of some smooth function phi of x under the effect of other function f of x. Someone will ask why we integrate from minus infinity to infinity. I will answer. We will integrate from minus infinity to infinity to study the behavior of f of phi of x under f of x in L of the plane, not in some points. This function, let's phi of x be the Gaussian function. This Gaussian function. We can study the behavior of it in this point, or in this point, or in this point, or in this point, etc. The distribution is not to study the behavior of phi in this point is distinctly. the distribution study the behavior of phi here and here and here and here in L of the plane. In L of the plane, it distributes the effect of phi of x under f of x in L of the plane. Then the integral will be from minus infinity to infinity, not from 0 to infinity, or not from 0 to minus infinity. We will study the behavior from minus infinity to infinity in distribution. This means that the distribution studies the general behavior, or and the name comes from the fact or the idea that objects, this object phi, this test function phi, distributes. F of x, the kernel function of distribution f of x distributes its effect on phi of x from minus infinity to infinity. F of x distributes its effect on phi of x in the interval in the plane from minus infinity to infinity, not from 0 to infinity. It will special case of distributions. That's what we mean. We mean by the distribution. I will show an interesting example and the famous example of distributions. Dirac delta function. Dirac delta function is a distribution. It's not an ordinary function. Dirac delta function defined by, let t sub f of phi equal to minus infinity to infinity, phi of x, f of x, d of x be ordinary distribution equal to phi of 0. That's interesting. If the distribution of phi of test function phi equal to the value of phi in 0 in identity, then this distribution called t of f is called delta naught, which is Dirac delta function. Any distribution with this property, it's equal to the value of the function in 0, at 0, at the origin of the space. Delta naught of phi equal to phi of 0. This is the formal definition of Dirac delta function. This is the formal definition of what? Of Dirac delta function. The Dirac delta function equal of phi equal to phi of 0. That's intuitively, by intuition, it's we will this implies the definition delta of x equal to 0 or infinity. 0 for Lx is not equal to 0. Infinity for Lx is equal to 0. This definition implying after this definition, or comes from this definition, because Dirac delta function is defined only when phi it's defined only when we are dealing with test function in 0, then it's in 0 equal to what? Equal to infinity. It has a mass, has a value, real value. But when phi of x non-equal to 0, that lets the Dirac delta function is not exist. It's equal to 0. Nice.